All right, what's up, everybody? We're going to go ahead and go over homework 9 here, which is two questions on chapter 31 and then chapter 32 as well. I've gone ahead and titled this etc. as the topic for this chapter. That's because we kind of have a grab bag of topics here as we're wrapping up magnetism and really here sort of finally connecting the dots between some electricity and magnetism topics where we have our fully formed theory of electromagnetism. And then next week we're going to go into electromagnetic waves, which is light, and we're going to go and study light for the remainder of the semester and do some optics and talk about lenses and mirrors and things like that. So so this chapter this week and this homework assignment is just sort of a random assortment. So for those who are still working through this chapter, we'll go ahead and just take a look at them. Some of these problems will be vaguely related, but we'll just sort of talk about what topics are on display for each one. For our first problem, we have a light bulb that's attached to a variable resistor, and we have a variable electric supply as well. So it's an RMS, a root mean squared. That's how you know that it's a variable supply. And then they also, I think, say it explicitly at some point that you have they also give you a frequency for 60 hertz. Okay, so we're going to vary the inductance on this thing. That is the thing that's allowed to vary. And ultimately what we want to do, first of all, is we want to have a rate of energy dissipation. That changes by a factor of 6. A rate of energy dissipation is, of course, the power. That is our rate of energy dissipation. And we want our power at some time as a rate to the maximum power to be equal to 1 over 6. And we'll go ahead and call this the minimum. So in essence, our power is going to vary between some maximum and minimum value as your electrical supply is allowed to vary. And we want to know what the difference is for the different inductances between those two states. Okay, so power is good. Ultimately, we want to relate power to something going on within the circuit. I know from last week that we can relate the inductance to the current using the reactance, if any of that rings a bell. So I know that power will also relate to current. I know that power is going to be I squared R. And so we can relate the powers here to a ratio of the current squared. So it would be I min squared over I max squared, because again, power is I squared R. And then the next thing is we want to replace our current with something to do with the voltage. So I know V equals IR. This is what we started with. Now when we have a variable EMF, we typically write this as an epsilon for the V is equal to I times Z for the impedance, which takes into account an inductance and a capacitance as well as a resistance. Okay, so in this problem, what's going on is our EMF is going to be held constant. It's a 120 volt RMS. So the EMF is going to be the same at both the minimum and maximum. And what's going to happen is as we turn the current up, or rather I should say as we turn the impedance down, the current will go up. And when we turn the impedance up, the current will go down. So all that is to say that the minimum current is going to correspond to a maximum impedance. Okay, and as we rearrange this equation, we'd have that the current is equal to epsilon over Z. So I'm going to replace this with epsilon over Z. Now this is going to be Z maximum on the top. And this will still be squared. And then on the bottom, we're going to replace our I max with epsilon over Z minimum on the bottom, quantity squared. And as I mentioned, that epsilon is going to be the same for both. We're only changing the inductance, and we're looking at how the current changes, but the RMS voltage is still 120 volts in the problem. So we can cancel those out, and we can simplify this, clean this up just a little bit. I'm going to take this ratio here, 1 over 6. And I'm going to set this equal to whatever's remaining over on the right-hand side there, which to clean that up just a little bit would be Z min over Z max, and they're both inside of a square, so we can go ahead and just put the whole thing inside of a square there. All right, so last thing we need to do is talk about the corresponding impedances when we are at a maximum versus when we're at the minimum. One thing that I know for sure is that my impedance is the smallest when I'm at resonance, and resonance occurs when the inductance and the capacitance cancel out and we're left with just a resistance, right? So the smallest value that Z can ever take, just to say that again, the smallest value that your impedance can ever take, which would be our Z min, is always just going to be the resistance, R. And then on the bottom, we have the maximum impedance. Our maximum impedance will be at the current that's given, the maximum inductance as well at that point. Now keep in mind the way that we add these together, going back to the last chapter, is that resistance can't just be directly added to omega L, which is the reactance of the inductor. They can't be directly added. Remember, we had to add them because they are 90 degrees out of phase. We had to add them in quadrature. So that's why you end up with this guy here, r squared plus omega L squared. And then this whole thing, well, this will be under a square root, but then we will ultimately square that square root, so we can just sort of collapse this square onto the r, and that should be good enough to solve right there. And so you just set that equal to 1 over 6. What do we plug in here for all of these variables? Let's see, I believe they're going to give us a resistance, or we don't have the resistance given immediately, but we do know the voltage, the RMS voltage, and we know the light bulb has a power given as well. So the resistance for that light bulb, if we were to solve here, how would we write this? Let's see. The resistance is going to be equal to voltage squared over power. So power is equal to V squared over R. Yeah, power is equal to V squared over R. Okay, so we're going to get our resistance. They tell you the light bulb is rated at a certain voltage and a certain power. So you'll plug in the voltage that it's rated at right here and the power that's rated at right here, find the resistance, and then you can plug that in to our equation. The omega given is just the frequency given for the electrical supply. Keep in mind that frequency is given in hertz, so you need to multiply by 2 pi to get omega, but then you can plug that in as well, 2 pi times the frequency given, and then you can solve for the inductance in that problem. Part B, they ask what the maximum resistance of the variable resistor will be, and for part B, I think we've actually, let's see, we found the resistance for the light bulb right here. If we want to solve for some maximum resistance, what we need to do is institute a resistance in addition to the resistance of the bulb. Okay, so we know that there is some resistance for the bulb. What I want here is I want to add in some other resistance, which we can call whatever. I think they're asking us to call it what is the maximum resistance of a variable resistor. So in other words, if we plug in a variable resistor as well, if we plug in the variable resistor, then we just add its resistance directly to the bulb rather than doing a quadrature like we did in the last part. And we want this ratio to the ratio of just the bulb by itself to be equal to that same 6. So again, this will be the resistance that we found in part A. You go ahead and plug that in there and just solve for the resistance of the variable resistor right there. I don't think we have to do anything else there. Nope, that should do it. Ultimately, of course, this is a ratio that will be equal to the square root of 6. Why is it equal to a square root? For the same argument that we had on the previous problem, where we had this whole quantity was squared, and that's equal to 1 over 6. So we're sort of flipping that relationship. So just make sure you have like a square on the left side or a square root on the right side to solve that problem. All right, variable resistors, variable inductors, that's kind of it. Just had kind of one problem on that, and sort of move on there. Onto our next problem where we talk about transformers. Transformers is a little bit more common of a topic than the stuff we were talking about in the last page. The way a transformer works is you have 2 coils of wire, and we use inductance. Remember, when you change the magnetic field through one coil, you'll induce a current in the other. That's what a transformer does. You have a transformer probably connected to your laptop, the little block that's on your laptop cord. Typically, you have that little block because there is a certain AC source that's coming out of the wall, and your laptop will be rated at a different AC, and so you need a little block that's going to change over the RMS voltage and give you something that your computer can actually use to function. Okay, so what is our rule? The rule is actually real simple. Again, you have 2 coils. One will be called the primary, one will be called the secondary, and what we'll have is a ratio of the number of turns. The number of turns in the primary versus the number of turns in the secondary. is going to be equal to the voltage in the primary over the voltage in the secondary. And so for part A, I think they give us the primary voltage, they give us the primary and secondary turns, they ask us to find the secondary voltage. So that's part A, is actually just plugging in the three things you're given for primary and secondary and solving there. Part B and C is to give you the resistive load of the secondary, and they ask for the current in the primary and the secondary. Okay, so in order to find the current, so for part B, we can just do, again, V equals IR. So the voltage in the secondary is equal to the current in the secondary times the resistance in the secondary. That's it. So they're giving you a resistance, which you'll plug in right here. You already have a voltage that you just found in part A, so you'll plug in your answer to part A right there, and you can solve for the current. So this is actually, I should say, this is actually part C. That's the easier part to do first. And then in part B, we need to correlate this to what's going on in the primary circuit in order to actually solve for part B. So for part B, we can rearrange this equation. We can come up with a different version that will relate the currents in the primary and secondary. And in fact, what it does is it actually flips the ratio on the right-hand side. So instead of doing number of turns in the primary over number of turns in the secondary and setting that equal to voltage primary, voltage secondary, instead it'll be current secondary over current primary. And then we'll have the current in the secondary that we just found, and we plug it in and solve. All right. So relatively straightforward problem. I do want to just reiterate though that you want to make sure you have these equations down for transformers for when you go to take a quiz, so that you can just quickly do any transformer problem if you were to come across any on the quiz. All right, now we're going to wrap up our study. We're going to move into chapter 32, which is why we're reorienting a little bit what we're doing. But we're going to wrap up our study of the different fundamental laws that are, equations I should say, that are collectively known as Maxwell's equations. So we've sort of covered them one by one, sort of jumped around. We had Gauss's law, we had Faraday's law, we had Ampere's law, and we sort of used them as we came across them in our study of electricity and magnetism. But now we're just going to wrap up a couple of loose ends. So the first thing is talking about the net magnetic flux through an object. So here's our rule. If you remember, as a reminder, back in, I think it was like the second week of school, we went over Gauss's law. And with Gauss's law, we said that you could have some net, I'm going to actually make sure that I call this the electric flux. You could have some net electric flux that was equal to the charge enclosed inside of an object over epsilon naught. And in Gauss's law, what that meant is that we'd have like a cube. That is not the cube that I want. Okay, let's do a cube. That looks something like this. I don't know why I'm drawing it in this order. Okay, cool. So we have like a cube, and you could find the net flux by finding the flux through each side and then adding them all together. I'm hopeful that this is reminding somebody of reminding you of the process that you had to do. We're not going to do it again. But the point that I just want to make is that in electricity, in that chapter 23, we could relate the net flux to some charge enclosed. So you could have some little object in here that was like weirdly shaped that had, say, some positive charge. And if you found the flux through all the sides and add them all together, it would be related to the charge enclosed. Now the rule in magnetism is that your net magnetic flux is always equal to 0. Though the phrase you'll hear is that there's no such thing as magnetic monopoles. That just means that you cannot have just some positively charged magnetic stuff. You always have to have the same amount of positive and negative inside of any object. And so the net flux through any object is always going to be equal to 0. This is why we don't do an entire chapter doing magnetic flux. It's just a couple of problems. It's because this is the only rule that we need. Your net magnetic flux will be equal to 0. And so in problem number 3, they're asking you to put this to use. You have essentially 3 faces here. You have the flux through the bottom circle, the flux through the top circle, and then the flux through the really weirdly shaped side. And you just add them together. So the flux through the bottom plus the flux through the top plus the flux through the side has to be equal to 0. All right, And then they give you the magnetic flux at the bottom. They tell you it's directed outward. As a reminder, that means that it's going to be positive. So you'll have some positive number right here. And it's in milliwebers. So make sure we convert that to just regular webers. So it'll be 10 to the negative third. And then we'll have flux to the top. To the top, they tell me the magnetic field is directed outward. So that will also be a positive flux. And it'll be whatever that magnetic field is at the top times the area at the top. This is BA. The flux in electricity was EA, now it's BA. And of course you could also have cosine of the angle between the magnetic field and the normal line of the surface, and in this case they tell you that that's 90, so you have cosine of 90, which is 1. All right, and then you also have the flux through the side, and that'll be equal to 0. And so you just plug in. They give you this flux explicitly, they give you the magnetic field and the area for the top face, so you have to calculate those. And it's my face, not my screen. And then you just want to isolate the flux through the side, and that would be the problem. The sign on it will tell you if it's directed outward or inward. Positive is outward, negative is inward. All right, now we're going to jump into, I think we're going to jump into it right now, the idea of, oh yeah, okay, so induced current and the magnetic field that is generated by the induced current. Okay, so where to start? Let's start with Ampere's law, which had us define our is this Ampere? One sec. Yeah, okay, so Ampere's law, which I wanted to pause there because I'm not sure we've actually explicitly defined this. But integral of b dot ds is equal to mu naught times the current enclosed. This is where we got our equation that we used. That was like b is equal to mu naught I on 2 pi r for a straight line piece of wire. You'll notice that this is just our integral of ds. That's to say if we were to walk all the way around a circle and add up all the length on the circle, you'd end up with the circumference of the circle, 2 pi r, right? And so then you have mu naught I on the other side, and since the entire thing is enclosed, you just have that current I. Okay, so we're not actually going to use this definition exactly, but we're going to add another term onto Ampere's law to make it the Ampere's Maxwell, Ampere Maxwell law. And the Ampere Maxwell law takes this sort of a step above and beyond. And what it does is, it says that in addition to some actual current that is flowing, you can have something that is called a displacement current. And so this is an electric field in a region that would correspond to a current flowing if you actually had charge that could be flowing through the area. So the most common example of a displacement current is between the plates of a capacitor, where you have, say, a wire connected to your parallel plate capacitor and then a wire coming out. And I have some current here that is building up charge on my capacitor, and that same current's going to be over here with charge building up here. And what we have in this region is no charge is allowed to flow through the region, right? But what we do have is we have an electric field, and that electric field can be related to something called the displacement current in that region. That displacement current will be equal to whatever the current is that's flowing through the circuit. And the way that we relate the two is we say that the displacement current is equal to epsilon naught times d dt of the electric flux through the region. Okay, so there's a couple things to keep in mind here. There's actually two moving parts in this problem. The first is that we have to only consider the amount of the current that is enclosed inside of a region. So that idea of enclosing current is going to transfer over to the displacement current. And then the other thing is that we're just going to replace that I enclosed with this whole term. So we're going to put all of this together now. I'm going to write this all on one page. And we'll have that the line integral of b dot ds, which is typically going to be b times some perimeter around some region, will be equal to mu naught epsilon naught, both are constants, times d dt of the electric flux, which I'll go ahead and write as EA. And then the last thing is to remember that this needs to be just that which is enclosed inside of a given region. Okay. So we're going to put all of that together in this problem right here. In this problem, they actually give us an electric flux total, which is nice. So we could actually go ahead and replace this with just the electric flux that's given for problem number 4. And they give it to us as a function of time, which is cool, so we can just differentiate, and then bam, we have our rate of change. So this will just be equal to the coefficient there. Pay attention to your units. My units are in millivolts, so I know I need to multiply by 10 to the negative third. And then on the right-hand side, we're doing a region of, oh, actually, one more thing I need to account for, of course, is that we only want the enclosed region. So we are asked for the magnitude of the magnetic field at a radial distance, at 2 different radial distances. For part A, we're at a distance that is inside the radius of the circular region. So we're at, for mine it says 3 centimeters, and the whole region has a radius of 4 centimeters. So for the enclosed region, I need to include a ratio of the areas, okay? So on the right-hand side, I'll have mu naught epsilon naught. Why did I put that over something? Mu naught epsilon naught, the rate of change of the electric flux. And then the way that I'm going to account for the enclosed nature is that I'll have the area at, say, for mine, it's r equals 3 centimeters, so it'll be pi r squared there, over the area of the entire thing. So it would be your big R, which for me is 4 centimeters. That'll be another pi r squared. On the left-hand side, we have the b dot ds. As I mentioned, that's typically just going to be the distance around, so that will be b times 2 pi r. And r is, again, this little r at 3 centimeters. For part B, you can plug everything in here, and then you're just going to solve for the magnetic field. And I think you have everything that you need. For part B, they ask you to find the magnitude of the magnetic field at some other radial distance. Now it's outside of big R. So when we are outside, everything is enclosed. The entire region will be enclosed. So this is just for part B. This is going to go to 1. And so you'll just plug in your R value there, and you can solve. And what I will mention is that you can write up kind of a general equation here. You could solve for B, and it would be that B is equal to mu naught times, well, it would be sort of related to the magnetic field equation that we had a few, at the beginning of our magnetism unit. But I'm not sure that we even really, I'm not going to write down that equation explicitly. Well, I'll go ahead and write it. We'll use it on the next problem. Let's just go ahead and go to the next problem. Okay, so problem number 5. In problem number 5, we have an RC circuit here with a switch, and we've got a battery. We have a resistance given. Pay attention to the fact that that is in mega ohms, so that's 10 to the 6th for the units. And then we have a capacitor, and they tell us it's a parallel circular plate capacitor. They give us a radius. They give us a plate separation. Okay, so first thing is we're going to need to use that to find our capacitance. Excuse me, remember that your capacitance for a parallel plate capacitor is epsilon naught A over D, where A is the plate area. That'll be a pi r squared. And D is the separation distance. So that's the first thing you'll need to calculate. Next up, we're going to close our switch, and they tell us the electric field between the plates is uniform, great. And then we're asked at a specific time, at t equals a specific time, they're asked for the magnetic field within the capacitor. Okay, that is important because we know that when we see a specific time given, we're not going to be at an extreme. So remember, with an RC circuit, you can have right when the switch is closed or a very long time later, but if they give an explicit time, that means you have to use your e to the negative equations. So great. So ultimately, the equation that we can use for the current in an RC circuit is that the current will be equal to epsilon over R times e to the negative t over let's see, it's T over tau. I'm trying to get this all in one run here. Tau is R times C. Yeah, so T over R times C. Okay. So how do we use this equation? Well, I know my epsilon is 5.4. I know that my resistance in the battery, sorry, the resistor is given, so I can calculate both things out front here. And then I will have found my capacitance, and they give me a time. So I can actually plug in everything on the right-hand side here, and I can get the current in the circuit at the time that they give me. And then once I do that, the only thing left to do is to find the current at a location within the capacitor. So here's what I know. If I have a capacitor, let's say that I have a parallel plate capacitor that has a radius, we'll call big R, the radius of the entire capacitor is 5 centimeters. Okay, what I know is that the displacement current inside that capacitor at 5 centimeters, I should say specifically, at 5 centimeters, the displacement current will just be equal to the current within the circuit itself. So I can actually just calculate the current right here and plug it in. Now, if I'm inside, I need to do a ratio of the areas like I did in the last problem because I only want the current that is enclosed. So for a little r less than big R, my displacement current will be equal to whatever this I is times a ratio of the area enclosed, which will be a pi r squared for the little r, over the area total. So again, just to write that kind of explicitly, it would be I times, my pi's will cancel out of both sides, and we'll have little r squared over big R squared. And so we don't actually need to come up with any other sort of expression. We can just sort of plug this in, and this will be our displacement current. And once we have our displacement current, they want us to relate that back to the magnetic field. So the last thing to do is just to say that our integral of b dot ds, which we know is just going to be b times 2 pi r, is equal to epsilon naught, mu naught, times the displacement current that we find right here. Okay, so I should put displacement current enclosed because we're truly accounting for the enclosure right here. But anyway, yeah, so we go ahead and calculate that. We have our current times this ratio, and we can plug that in, and then just keep in mind that we're plugging in the radius for the location within the circular parallel plate capacitor. All right, and that's it for that problem. I think we have one more, or we might have two more here that deal with displacement current. And the next one, we're given a graph, and the graph has a changing electric field. And we are asked to find the displacement current in terms of the electric field. Okay, so I have a definition for my displacement current. It is epsilon naught times the rate of change of EA, where either one of those things changes, that is only enclosed. This would be for the enclosed displacement current, but we're going to make sure, for this problem it's not going to matter. Let's see, the calculated, yeah, they asked us just to find the displacement current through a region with a given area, so that it's all enclosed in this problem. In other words, so the only thing we need to do is consider what is the thing that's varying. Well, we're given a constant area. In our graph, we can read off the dE dt's. Now, one thing that I want to mention that I have sort of been cavalier with so far, because it hasn't really mattered, is that your displacement current is going to be related to an inverse relationship, a negative sign. The negative sign will matter in this problem, so we just want to make sure that we're incorporating that. And anyway, so let's go ahead with the problem. All right, so as I mentioned, everything is enclosed, so we don't need to use any sort of ratio for some enclosed areas. Everything's just going to be equal to 1. And our area is going to be constant, so we can pull that out. We have negative epsilon naught A times ddt of the electric field. The only thing that we actually need to calculate in this problem is the rate of change of the electric field. It's going to come from my graph. What is the time derivative of an electric field? Well, it'll be dE dt. That'll just be the slope on the graph there. So you just read those slopes off, doing a little bit of geometry, and you'll plug in the slopes for the 3 different regions. This right here will become the slope. Keep in mind that a downward, that's a little messy, downward sloping line is going to give you a negative slope, and then we'll have a negative sign out in front that will cancel that out. Make sure you're not missing any problems there. But you just do that for each of the three regions, and then again, your area is a constant that's given, and we already know epsilon naught. Also pay attention to units. The time on the horizontal axis is given in microseconds, so that's 10 to the negative 6. And other than that, I'm going to trust everybody to be able to find those slopes. All right, and then we have two more problems that are going to both have to do with torque and electrons. I think it's electrons and atoms and magnetism inside of objects like that. All right, so the first one is we have an electron placed in a magnetic field that is directed along a z-axis, and we're going to have a parallel and anti-parallel alignment for the z component of the electron spin magnetic moment. Oh my goodness, electron spin, we're bringing that into play. Well, actually what we have here is something called the Bohr magneton, which is the electron placed inside of a magnetic field. And the energy of the Bohr magneton is just going to be equal to let me get that equal sign a little bit better. It's going to be equal to the magnetic dipole moment of the Bohr magneton times the magnetic field. This should look kind of like mu b. Remember mu cross b? The torque was mu cross b. To go back to when we had a loop that was placed in a magnetic field, the torque there was mu cross b. The energy that is related to that torque is just mu dot b, so that's where this sort of comes from. Okay, so yeah, so this is the dipole moment for the Bohr magneton, which I've used sort of an inconsistent subscript for it. Let's actually just put Bm on both for Bohr magneton. And then the Bohr magneton has a constant value. It's EH over 4 pi m. And we have times magnetic field. And in fact, because these are all constant, this is going to be equal to 9.27 times 10 to the negative 24th. And the units here are joules per Tesla. And this is just the value of the Bohr magneton. And this, another way of saying this is that this is the dipole moment for an electron that is in a magnetic field that has some spin. And yep, so you just plug that in. In this problem, they ask us for the difference between the parallel and anti-parallel moment. Well, in truth, we would have had a negative sign out here. So the delta U between parallel and anti-parallel is going to be equal to a positive version of this minus the negative version, which is actually just 2 times mu sub b times b. And as I mentioned, the Bohr magneton has this given value. You just plug that value in. There's not a whole lot to this problem. You're just going to plug that in and plug in the magnetic field that's given, and that will give you the energy difference between the two different alignments. Okay, it's a very kind of random one-off problem, but one that does show up on a final exam every few semesters, where you just need to, oh, that's a Bohr magneton. If I have an electron with some spin and stuff, there's a Bohr magneton present there. All right. Last problem here then is we have an iron bar. Cool. So we've got a chunk of iron, and they tell us the dipole moment of an individual iron atom. So that is, again, a mu for, I guess I should say Fe for iron. And they tell us that it's 2.7 times 10 to the negative 23. That was supposed to be a 2. Joules per Tesla. And we are asked to, first of all, find the dipole moment of a bar of iron that has a certain dimension. So this is the dipole moment for each atom. If I want to find the dipole moment for an entire bar where all the atoms are aligned, and what I need to do is find how many atoms I have and multiply this by the number of atoms to get the dipole moment for the entire bar. So how do I find the number of atoms? This is actually probably more of a chemistry question than anything, but what we know is we can find the density for iron. Oh, it's actually given to us in the problem. They give us the density of the iron, and they give us the molar mass. And I believe with those two things in our pocket and Avogadro's number, you can find the number of atoms in the iron bar. And then you'll have mu for the bar is equal to the number of atoms, which will again just come from doing the dimensional analysis with the size of the bar times the mu Fe, the dipole moment of the individual iron atom. Great. And then for part B, we're asked to find the torque that we need to hold the magnet perpendicular. Okay, so for part B, we're going to apply some torque. And I know that the torque is equal to mu cross B, which is mu B sine of phi. And since I'm asked to hold the bar perpendicular, that means that we'll have mu and B perpendicular to one another. So this phi right here is going to be actually 90 degrees. But once that's equal to 90 degrees, then this whole thing right here goes to 1. So you'll just have mu times B, and your mu will be whatever you found in part A, and then B is the magnetic field that's given to you. And so you go ahead and do that calculation as well. All right, so that'll do it for this week's homework section. Next week, I believe we're finally going to get into lights and optics and stuff like that. You do have a quiz on this stuff this week, though. If you have any questions, feel free to let me know, and I'll see y'all soon.